Hello, welcome to Happy Hour with Architects. Today we will talk about network architecture co-design. Recently we have this revolution in networking with programmable switches and smartNICs, and this has introduced a type coupling of networking and architecture or systems. So network cards and switches now are capable of performing not only network functionality, they can perform some computation in the network. And today we have two perfect guests to talk about this particular topic. Our first guest is Alexandros Daglis, who is a professor at Georgia Tech. His background is in computer architecture. But he's the first few people in our community who was looking at this tight coupling between network and architecture. And actually his thesis is all about it. So this is why he is the perfect guest today to talk about this topic. Thank you for coming, Alex.
Thank you for inviting me, and thanks for the very kind introduction.
So our next guest is Muhammad Shahbaz. He's a newly minted professor. He will join Purdue University next year. And currently he's a postdoc at Stanford University. And he's coming from this networking background. And he has been doing a lot of interesting work on smart NICs and smart switches. And that's why I feel that from his networking background to combining with systems and architecture, that makes him a perfect guest today to talk about this topic. Welcome, Shahbaz.
Thank you for having me, Samira. Thanks.
So my first question to both of you will be that both of you you started from a very different point, right? Like Shahbaz had these pure networking works and he was very much doing that. And Alex, you have these systems and architecture background, but then you two kind of converge to this same point that now both of you are kind of looking at these network and systems, network and architecture. So I would like to know that how that transformation happened, like what motivated that, and what's your personal story to converge to this point?
Okay. Should I start?
Yeah, go ahead.
All right. So actually, it is an interesting story in the sense that it started very early in my PhD. I started a PhD thinking that I want to focus on memory systems, especially cache hierarchies. But then during my first year of my PhD, I investigated a couple of smaller projects, and the one that captivated my interest was this observation that you have this divide between scale-up and scale-out architectures. And typically accessing the memory of another machine on a scale-out architecture is so much slower than accessing the remote memory in a scale-up architecture, right? You access memory of a nearby socket, maybe you add 100 nanoseconds. So you typically don't care that much about locality. And then if you looked at the architecture trends back around a decade ago, you started having these micro server architectures like HP Moonshot, for instance, was a good example of it, where you have a box of servers with a very high bandwidth, low latency backplane. So the fabric itself is super low latency. So we wondered, how come it's so much more expensive to access remote memory in such a scale-out architecture, even though the box from the outside, the box is not any different from a large multi-socket server. So the question we wanted to, the research started with a question: how fast can we make remote memory access in a scale-out architecture? And it turned out that it's not really rocket science, right? You just boil down, you dissect where the latency comes from, And we realized, hey, yeah, it's a completely different protocol. You don't just issue a single load and store, and the hardware determines where to route it. You run a whole network stack. And then the second source of overhead was the interface itself, right? So the way you interface to a scale-up machines network compared to how you interface to a general network in a scale-out architecture is very different. One case is typically glueless. The other one is you have to convert. Like in the scale-up case, you have this unified format of memory transfers, right? Everything is a cache block. Everything in the system talks in the same language of a single cache block. In the other case, every server is built to interface a generic network that has a different transfer granularity. You have to pack, you have to unpack. You have basically no assumptions about what the network will guarantee. So the network that you use, the network stack you use to talk to this network is a lot more heavyweight. You need to account for packet drops, packet reorderings, this, that. Right? So, so if you can give stronger guarantees from the fabric itself, you could actually build a scale out architecture of a potentially a smaller scale, of a smaller scale, right? Right? Not, you don't build this architecture to scale to a wide area network. Let's say you have this one box of servers, this one rack. You still want it to be a scale-out architecture. You can design a protocol and you can design a direct interface of your server to that network so that your performance practically converges to that of a scale-up architecture without all the complexities of the scale-up machines, which are typically associated with hardware coherence. So that's how it all started. We asked that question. We thought, okay, hey, let's design a scale-out architecture, see how fast it can be. And yeah, it turns out there is no real fundamental difference between the two. You can build actually a cheaper scale-out architecture that can access remote memory as fast as a scale-up architecture, as long as you design a lightweight enough network protocol by relying on some stronger guarantees from your fabric. And as long as you specialize the interface. In our case, we determined that you can actually, if networking is one of your first order performance determinants, you might as well treat the network as a first-class citizen, right? So your network interface is actually should be a non-chip accelerator. So you talk to your network interface directly, and that taps directly into that network. So you cut all the latencies associated with jumping on and off an I/O interface, which is what traditional network is, how a traditional network is interfaced, right? So you have a PCI interface and you attach a network adapter there, and you spend like a couple of microseconds just on that transition. So that was the beginning of the project, and that started my whole dissertation and my current research direction, right? So once you actually start designing the network as if it's a direct extension of your compute resources, what stops you from actually co-designing the two and start blurring a bit the boundaries of what is really the network's responsibility and what is your compute the responsibility of what is traditionally perceived as the compute resource, right? What do you have to do? What do you do on the CPU just because you didn't have any other compute resources to play with, versus now an architecture where you're as an architect are co-designing both the tap into the network, like your network interface endpoint. I'm not talking about switches at all here yet, right? And that's a little bit outside of my current expertise, but we're also getting there. I guess Shahbaz may have more experience in that. So once you start co-designing the two, you have the luxury to rethink some abstractions and think, what is it that is running on a CPU just because from a legacy perspective it had to run there, that I can now take and do it more efficiently just one step closer to the network? And what are the new interactions I can have between my network, each server's network endpoint, and the CPU that can actually make the end-to-end performance better. And I can keep talking about like next steps about this, but I should probably
yeah, I think we will talk more about this integration, like NVIDIA buying Mellanox. But for Shahbaz, like as a networking person, did you like when did you make the switch? Like I feel that this tight coupling, it's very new, right? It is very new.
Yeah. So I think for me, basically, if I think of it, how I ended up being where I am and the kind of research I'm doing. So I did my undergrad in computer engineering. So I had a hardware background since before starting my PhD. And there, what we were doing was like my first interaction with networking was, okay, we have these fixed function giant boxes. And we want to add some other, like some more functionality to it, like so do some like in-network filtering or something. And the idea there was like, okay, just pick up an FPGA, connect it to a port, and then do that thing there. So that sort of works on very specialized cases. Like if you have a very precise workload that you want to do, or do some specific like DDoS attack and things like, so middle boxes are like a thing that people talk about in this scenario. But when I started my PhD, what I found was actually today, like in the past, what we had was like, we were okay with, given the size of the network we used to have, we were okay with these fixed function devices because they were designed in such a way that you can still meet the line rate invariant of a network. And the question is like, when did this line rate invariant came in? Nobody knows, but it was such a thing like, okay, as a switch, I'm going to do this thing very, very fast in a very predictable amount of time. And that's what I'm going to do. There is no variance in there. Whatever I will do is going to be precisely done for each and every packet. So I think the main idea there was like, okay, let's sort of push this sort of variability in the overall design to the end host and let the network be as predictable as possible. And with the line rates, so as the data center, like as the networks were getting larger and the line rates getting larger, the typical like CPU-based switches were no longer able to keep up. So we wanted to have these ASIC-based, very dedicated switches that are running at high speed with a very fixed logic in there. But moving forward now, what happened is like these data centers now are so huge. Like look at Amazon, look at Microsoft and all this. Like running them is becoming very hard, very difficult. Like you want, like if you have a collection of like tens of thousands of these switches all interacting with each other in a distributed manner, what are they doing? How are they interacting with each other? How are they routing with the traffic within the network? Are they able to meet certain sort of SLOs that we want to define on these in these kind of networks? So the problem that came up was like, we need much more fine-grained management and control on these devices. So this is where the first interaction of the networking folks came in with the actual switch. Like, okay, previously it was a black box. Everybody was building their solutions surrounding that black box, coming up with like protocols to sort of route them through the network. But then when this management piece came in, the SDN thing, like if you remember like 10 years ago, software-defined networking came about as saying, let's take this sort of the control element of these devices out of these big like scale up like machines and then move it out to a centralized server. And then let the networker define like how for each incoming packet, what do you want to do to it in a centralized way and then route it through the network. So that was good. Like it gave us a little bit more fine-grained control on how the networks are working. But still, the thing was like these devices, we call them in a notion like these were still fixed function. They were just operating on a fixed. So the notion of a packet was still predetermined, like it's an IP packet or a TCP packet, and you are just restricted to functioning on these fields itself. What if I want to add a new field? What if I want to do a certain new kind of protocol that is not defined in these existing collection of protocols that are out there? So that is the next step that came in. Like given that with SDN, you can manage these devices which are operating on these fixed function headers, but if you want to add something new, you still cannot do that. So that is the piece that when I started my PhD, that intrigued me. And then I started working on that particular element. Like how can you enable these, again, line rate devices? They have to meet a certain line rate goal that, oh, you cannot just say, you just replace these boxes with FPGA. No, because the rates at which you are running, like terabits per second, you just cannot achieve them using FPGAs today. So the question was like, okay, how can we then enable these devices so that it allows us a very specific kind of programmability So that, for example, if I want to add a new header, I should be able to do that. It's not a very general purpose processing. It's a very specialized task. And can I devise an ASIC that can allow me the capability of adding these new headers? So think of it just like the switches that you have today. You can update a new rule in them. So I think of it as a programmability part. Like, okay, adding a new rule is sort of a functionality that I am giving to the programmer that you can program me by adding something new. What if we can extend it to letting them add new headers? So how can you do that? And what kind of abstractions can you enable in these devices so that you're still running at line rate with the same power budget that you have with the flex function devices, but still be able to do more in there. So that is sort of where things are heading in mind. Like from the networking people, when you talk about them, okay, how your interaction came up with the architecture is about like, we wanted to have more management and control on these devices. And the idea was like, can we actually do something like what other people have done in the area of GPUs and DSPs, where they came up with these domain-specific devices, which are not general-purpose CPUs, but are designed to do a very specific task very, very efficiently. So thinking of networking as a domain, can we come up with a sort of a hardware, again, a domain-specific hardware that can do these functionalities? So this is where we are heading, and this is where how the sort of networking is trying to combine. So if I put it in a bigger picture, the way I look at it is, today, if you see, we are seeing in the architecture space that people are trying, so they already have general purpose CPUs, but what they are doing is they're going towards domain specific architectures to gain more performance. And in doing so, they may be willing to sacrifice some flexibility. So if being on the networking side, I'm seeing a similar trend with opposite goals. So on the networking side, we were always line rate high performer. We never had issues with, oh, there's an issue of performance, but we were very fixed function. It was highly unflexible. So we are going towards domain-specific architectures now, not for performance, but for flexibility. How can we define these architectures that let us do certain kind of sort of operations or additions to the switch without requiring us to buy a whole new switch and then do a forklift upgrade, like replace all the devices and put in a new one. And then I think, so this is where we are, like, this is where the sort of the intersection of architecture and networking is happening in my understanding. And moving forward, I think one of the open areas in networking right now are, what are the new set of abstractions or primitives do we need? Because we have only touched the sort of the tip of the iceberg here. Like, okay, you can add a new protocol, you can match on these different new headers, that's fine. But what more can you do? And to the point of Alex, this thing about like moving compute into the network, what more primitives can we enable in the network? Again, keeping in mind the line rate invariant, like we need to run at line rate. We simply cannot just say, replace a switch with an FPGA or a CPU. So with that constraint in mind, what more primitives can you enable in the network so that they can help you do more, like offload more compute from the end host? And the reason why this is important now is because if you look at like Amazon and Google, like the problem is typically nobody is talking about throughput anymore. Like throughput is now not an issue. The main issue is the tail latency. The worst case latency of all the nodes that are performing like service, they need to finish in a very predictable amount of time. And being like looking at these data centers, we have end host, and a lot of work is being done today on the end host to sort of ensure predictable tail latency and so forth. But if you look at this entire data center, we have these switches sitting there, like tens of thousands of them. Why not make them a first-class citizen as well and let them participate in the compute? So I think that's the thing that excites me today. And I think hopefully moving on, this is where the convergence of architecture and networking is going to happen. And we'll see more and more workloads. So again, I can move on and talk more and more about it, but let's move on and have some Q&A. Yeah.
No, I just want this to be like a very informal chat. So one thing that piqued my interest is this constraint of line rate. But if we offload some functionalities in the network, do you think we can kind of relax that? Is it possible? Like, what's your opinion?
So my understanding is like when we say line rate, we are not assigning a sort of a specific number to it. Like I'm not saying terabits per second, or I'm not saying 100 gigabits per second. My understanding of line rate is like, once you say my system is working at this speed, it should always work at that speed for all the packets. So if I design a switch and it's a 100G switch, it should operate at 100G with the predictable latency of n cycles for each incoming packet. So that's what I mean by line rate. And then depending upon whether you're sitting at a core that might require terabits per second processing, then you have to run at those speeds. But if you're top of a rack switch, you can actually relax that constraint and may run at a lower speed, because again, it's connecting to just a bunch of servers and then going upstream through a 100 gig interface to a spine switch or a core switch. So basically the line rate sort of is defined by the location of the sort of the network entity. So for example, for a smartNIC, the line rate is 40G today. Like if it has a 40G NIC, then it has to actually operate at those speeds. But just to point out again, like I think my understanding of like when we talk about these switches and the difference between an end host and a switch is what we assume or expect from the switch is like it's always running at a speed that it has given me on a data sheet, and it's always finishing all my packets in those many cycles with the exact same latency. But when we think of end host, we never think in that sense. Like, okay, we'll send it to this. We hope to have an average latency of something or an average throughput of something. But in switches, there's no notion. Like average is always the same as the min and the max.
Right. So essentially, my understanding also with switches is that they have to give you this guarantee, and as soon as they lag behind just a bit, queuing can grow so rapidly that it can destroy the whole data center's performance, right? And then it has cascading effects. So if one of your switches starts misbehaving and not delivering line rate, that will propagate. You will have a horrible congestion across the data center. And then, well, good luck converging back to operating performance, especially if you care about day latency, right? And the latency is the killer metric these days.
Yeah. And I think this is a good point. Like the queuing is something that is there, and that like definitely affects the performance of the end-to-end latency of your system. So again, that is something that comes in there, and you need
I
to
guess
design
let's say
some
hi. Hello.
Yeah, hi. Here's my son, Adi. Yeah. All right. So I agree with your point. Like so, again, congestion and queuing is something that is there. But again, that's sort of like, if you think of from the architecture point of view, from the switch as an architecture, sorry about that. As like from the bare bone architecture standpoint, like the switch has to give you certain latency. But these congestions and queuing, these are sort of thought of as a high level thing that is running on top of them. Like this is typically handled separately from when you're designing a switch. It's sort of like it's like end-to-end thing where you define, okay, when the packets are going in, if they're coming in and they're contending for a certain port, how do you schedule them, and the scheduling logic, and how do you define priorities and so forth. So that's more like a dynamic sort of aspect of your network.
So my understanding is, if I think about NICs, then the type coupling is kind of different. Like it's more like how we run the software stack, how it will impact the tail latency, and can we move it to the CPU or tightly integrated close to CPU. But when we are talking about the switch, then it's a whole lot of other issues, like what should be the interface, what type of programmable operation we want to provide, what type of background accelerators we want to have. Yeah, I think it's actually pretty exciting. Yeah, if I think about that, like how many things we can innovate, it seems like it's a really interesting topic, and more systems and architecture people should be really interested about it. So one particular thing I want to ask your feedback is like NVIDIA buying Mellanox, right? So GPUs are now highly popular for running all these machine learning workloads. And typically the models are getting so big that there are multiple GPUs talking to each other. So what do you think will be the current industry standard or the future industry standard that we will see very soon? Or how this will impact both networking and architecture?
Well, you said it. I think the reason why that was a strategic buy is distributed machine learning, right? That's where the money is, and it's about scaling it out They need the bandwidth, definitely, and they need the latency. Who's better to buy than Mellanox, who has been a pioneer in RDMA, high bandwidth, low latency networking. And I don't know if part of the strategic goal is to create an interface lockdown, right? Instead of having of designing a general interface that would be potentially usable by competitors. Like, let's say they design a new, like we have PCIe, they design a new standardized interface just for these GPU RDMA architectures. Maybe they will, like they have designed NVLink, right, for the NVIDIA GPUs. There will be a more scalable proprietary high performance interconnect architecture that that they will monopolize, right? So that it's not like NVIDIA needed the help to dominate the machine learning the machine learning market, but I guess when you're ahead in the game, you need to be strategic to stay there. So yeah, that's my take.
Yeah, I think that makes sense. Like the thing about the vendor lock-in, because if you look at the reason for them to buy, like one of the reasons, like they want to provide a full stack solution, like an entire rack composed of GPUs connected together with very low latency and high throughput. So that might be one thing, and they're looking for a very tightly integrated design where they give you the best possible latency. How, like, again, it comes back to the point of a scale-up solution rather than a scale-out solution. So I don't know how that will pan out in the future, but yeah, it seems like that's the sort of the strategic play here.
So go.
I wanted to bring up an interesting point about line rates that we were discussing before. So from the less from the switch perspective, more of a nodes perspective. An interesting trend is that, and we've been talking for half an hour and nobody mentioned Moore's law, so I feel a bit uncomfortable about that. So I have to mention this, right? So if you look at how CPU performance evolves and memory bandwidth evolves, and on the other hand, you see how network bandwidth evolves. At least from the roadmap's perspective, the network bandwidths are alive and kicking, right? While the more on-server metrics have stagnated over the past few years. So it is a growing concern for server designers. So if you give me a 1 terabit Ethernet cable and I stick it onto my server, what am I going to do with that bandwidth, right? It's good I have it, but can I actually use it? So if you do the math, that gives you only a few hundred, maybe a few thousand cycles per packet for a CPU. And it also, 1 terabit per second also represents a significant fraction of your memory bandwidth, which, traditionally you wouldn't even think about it. You might as well, you have a 1 gigabit Ethernet, you might dump that network bandwidth 10 times between your memory and your CPUs, and still you wouldn't have a bandwidth issue. Now, you have, once the network bandwidth starts approaching your memory bandwidth capabilities, even though it will still be significantly lower, but how efficient you are in moving this incoming bandwidth within your memory hierarchy starts becoming actually important. And how do you actually guarantee that this data transfer from your network endpoint, your 1 terabit network endpoint, within your memory hierarchy will be efficient? You need to do co-design, right? You cannot design the network as a delivery endpoint, and I'm a host and I just dump data into that memory location and I don't care what happens to it after that. You have to transform this mentality and actually think end to end. Where does this data come from? Where does it want to end up within this deep and wide memory hierarchy? And what is it going to trigger in terms of response, right? If you can also go another step, like further, usually and if we talk about data centers, usually you have this request reply pattern all the time, right? So you might as well think about it in that way. If you're about to do a co-design, you have this massive traffic coming in, requests, and there will be an equally massive traffic going out, responses. How can you design this whole loop in the more efficient way to minimize data traffic and also cut latencies? Because you only have a few thousand cycles per packet if you want to operate at the line rate. Of course, you can have 1 terabit per second and only use 10 gigabits per second, but that would be a waste of your resources. So if you want to squeeze performance out of it, you want to start thinking about co-design.
Yeah. And I think one of the things that is happening today is like this notion of smartNICs, where they're thinking of adding more and more cores on the NIC so that it can help offload some of the computation, basically from the network standpoint, like moving some of the network stack down into the NIC and then terminating these connections and then sending only the data to the CPU. In some sense, reducing the amount of traffic that was going to the CPU without those smart NICs. But the interesting question there is like, it's still a fledgling space. It's not clear how it helps actually to go from a very high speed beefy core into a very wimpy core sitting in a smart NIC, because eventually you're sort of reducing the size of the pipe by adding these sort of cores like ARM cores and like other cores like RISC-V and so forth on the NIC itself. Because I think one of the things, like as you're going more and more high speed, you have to come up with a more and more domain specific kind of a design for these NICs, which is still, again, running at very high speed, giving you very tight end-to-end latency, but still able to do some of the functionality you need, rather than having a fully general purpose CPU sitting on the NIC itself. So the idea there is like, when you're thinking of like the compute and communication co-design, what are the kind of operations do you actually want to do on the communication part, like on the network or the smart NIC itself? And then I think the interesting research direction there is like, first of all, to explore what generality is there in these kind of workloads. Like, can we actually be more restrictive in the kind of architecture that we need to provide for them, because they're just doing some very specific tasks? For example, again, giving you an example of the network switches today, like the P4 switches or the RMT switches from Barefoot. They're just using a match action table as an abstraction, because basically what you want in a network is like, you match on some header fields and then you do a single action, which is just set some field to some specific value, like matching on an IP, set the output port to say port number 2 or something. So that's a very sort of, again, it's not a general purpose abstraction, but it's a good enough abstraction for people who are working in the networking domain, basically in the switching domain. So for, again, extending this all the way to the smart NICs, it's still not clear yet, because as a first step, I think what's happening is like, it's the same thing happened that in the networking space when people were trying to build switches, throw in a very general purpose device in there and let the people explore what they need on that architecture in the switches. Similarly, on the smart NIC, it seems like what's happening now is like, they're throwing very general purpose CPU cores on the smart NIC, and then they're saying, let's see what can and cannot we can do on these NICs. And then once maybe if there is a steady sort of consensus on what kind of operations we need, maybe then we will come up with a very specialized sort of ASIC for it. But I don't know, like I'm always amazed by this process. Like, is it okay to go through this process of starting with a very generalized ASIC, coming up with a bunch of different products, and then saying, okay, now go back. Now we have we have some sort of a consensus on what kind of operations we need. So let's revisit and build a new architecture. So it's still something that I'm not clear about. But again, I think in some mechanism, it's sort of like a chicken and egg problem. People will not actually write out like applications for SmartNIC unless they have this sort of functionality available. And the people who are building these architectures will not actually build these specialized architectures unless they see a need for that kind of workload. So the best, I think, combination right now, because again, it's a very starting, like an emerging space, is throw in these general purpose CPUs and then let the people explore what kind of things they want to do. Yes, you won't be able to meet the kind of line rates that is coming up, like terabits per second, Ethernet, and so forth. But that's a second step. First, we need to know what kind of workloads can and do we need on these smart NICs.
I absolutely agree with that with your thoughts. And I always thought that that smartNICs with general purpose cores do not make much sense. Of course, there are also the smartNICs with reconfigurable logic on them. So from a performance perspective, I think those make a lot more sense, because it's not, of course, you cannot just remove something from a Xeon processor and move it onto a simpler ARM, an in-order ARM core or in-order RISC-V core on the FPG, on the SmartNIC, and expect it to run faster. Yeah. Of course, it won't, right? So I understand that it makes a lot of sense from an exploratory perspective, right, to see what you can do there. So ultimately, there are two things that could help you if you do them on the SmartNIC, right? There are two opportunities, basically. One is location. Is there something that this change of location helps you do better, right? Instead of being onto the server, you are basically between the network. You're closer to the network than the compute resources. And the second one is different hardware, right? If the NIC features a different type of hardware rather than a von Neumann processor, can that piece of hardware do some type of computation more efficiently? Well, a good example is RDMA, right? I mean, you don't do anything magic. You just have an ASIC that terminates a specific network protocol, and that's why it is lower latency. So of course it makes sense, right? This is something that you want to do direct remote memory operations. It's reasonably general for applications that want to use that functionality, so you harden this into an ASIC. So people are now trying to extend this idea. What are other basic functionalities that we can remove from the CPU, put them onto the NIC, and do them more efficiently? I doubt the final form of the SmartNICs will be CPU based. It will have to be some specialized hardware.
But the question there would be, what would be the programmable interface, right? Like people like general purpose CPUs because you can throw anything there and it will run. But whenever we are talking about domain specific accelerators, like we have to think about how to still provide some sort of programmability. So I like the P4 community because they have provided this pipeline, but still it provides the opportunity to actually implement your own stuff. You can look at the headers, you can insert new rules. So my question would be that if we want to have domain specific functionalities in SmartNIC or in smart switches, like how should we actually come up with a programmable interface instead of not moving back to fixed functions, right? We just made the shift. So it seems like it's actually quite challenging. Like GPUs, these are very good example. Like even though they are domain specific, they are pretty programmable. So there is this chicken and egg problem. I guess I will agree with both of you again.
So again, I think, so if you look at what P4 has done, it's like I think they had an easy start. Again, not in terms of building a switch architecture, because it was a sort of a very, like, it was a conventional wisdom that, okay, if you want to gain more speed, you have to be fixed function. Otherwise, you won't be able to get the speed in the same power budget. So the Barefoot people or the RMT folks who wrote the first RMT paper, they actually demonstrated that today with at the technology scale, like I think 7 nanometer or things that are coming up, the logic piece of a switch is actually a very small component of the overall architecture. The most dominant part is first of all, is the memory, the amount of memory you need to place in the switch, because you want to keep you want to have big buffers and so forth. And also the amount of IO that you are pumping into in an ASIC that defines the size of your overall chip, right? Okay, how much IO do you need in and out of the ASIC? So what I have heard is typically that defines the size of your ASIC, and then based on that you see, okay, this is the total area I have. So then you try to sort of add in as much memory as you can on those ASICs, And then after that, if you look at the fixed function part of that switch, that is actually doing like IP routing, ACLs and so forth. It's a very small, like a very 1% or 2% like it's actually taking like 1% or 2% of the area of the overall ASIC. So what they demonstrated in the paper was like, if you make, because once you think of a programmable switch, what is actually changing in these fixed function switches? Memory is still the same. IO size is still the same. It's the fixed function piece that you're changing, and which is already very small. So if you replace that with the programmable logic, it just jumps from 1% to say 1.5%. So it's not adding more into the overall power and area budget of your chip today. So that was the first thing that actually demonstrated like, okay, this is doable now. Maybe not in the past, but now at the kind of like technology scale you have and the sizes of the chips you are building and the speed that you have, it's doable, because the programmable logic part, or the logic part itself, is not the main sort of dominant factor in these ASICs. Now the next step, that is like, so that is what they demonstrated, and that's how programmable switches start coming up now. Because what's there is like, nobody will actually buy your ASIC if you say you're taking like 2x more power and area. That's just not, I think, is not a selling piece. Like they won't buy it, because first of all, these data centers, if you talk to them, they have already sort of tailored their data center and tuned their data center using existing switches, and they've already written a large code base around it. It's very hard to replace all of that with a programmable one. So, and if on top of that, you're saying without coming up with a very sort of key use case that you replace them and you get some programmability, well, that's fine. For them, adding a new header, again, the velocity at which these headers are changing is not that fast. Like it's not like you're changing a header every other day. It's changing every 1 year or 2 years. So maybe it aligns with their sort of upgrade cycle. So again, so all these factors were there that actually you had to take into account to say why programmable switches are making sense today. So when I said like in the beginning, like it was an easy sell, was like everything was fixed function there. They just made it programmable. So IP routing was already there. They allowed you to do it in a programmable way that you can define your header now and do it. Now, like VXLAN headers, you had support for it. Again, it was fixed function, but now you can add a new header, say VXLAN version 2.0 or something. But they're basically, in terms of like, if you see the computing power, they're basically the exact same thing that was already there in a fixed function switch. Now, the next set of questions that people are asking, and what I'm working on now, is like, how far can you extend this programmability footprint? Like, what more can you do in these switches, which was not already there in the fixed function switch? What new primitives can you expose while still keeping this sort of line rate invariant that we're talking about in these switches? So that's the kind of, like, basically, what should be the instruction set, the future instruction? What should be the instruction set of these switches in the future? Like, nobody has sort of devised that at the moment, and still an open research area as to what is the ISA of these switches.
Yeah, I completely agree. Like, it feels like there is a lot of new things to do. Like, what should be the, like, first of all, what should be the interface to which is exposed to the clients? What should be the ISA within the smartNIC or smart switch? What type of compute capability we want? And I guess we are mostly talking about architecture and network, but there is also systems component involved, compiler, code optimization. A lot of things needs to be rethink.
I think what is especially interesting in these programmability of the network interface and the switches is really how much, in terms of defining a language for them, is really how much do you want to enable flexibility versus restrict flexibility in favor of performance? Because there is, whatever additions we make, they're really only for performance. There's the only reason we want to program them is to improve performance. So would you be willing to add more flexibility, more expressibility, if that expressibility will actually result in terrible performance? For instance, if a specific interface, like if I do a match and action architecture, and that's the only thing that I allow you to do, that by itself makes it much easier to meet performance goals. If, in contrast, I let you write a C program and offload it to some cores on the switch, and I can, if I enable that, it's good because it's easy for someone to program that switch, but the performance will be terrible. And the additional limitation there compared to, let's say, a single user environment, let's say we talk about one specific accelerator, is that a switch or a NIC is actually a gateway for a multi-tenant environment. So you don't want to really allow one application to offload something there to benefit itself and degrade the performance of everybody else who's going through that compute unit. So I'm actually in favor of some interface that is a lot more restrictive, but gives more guarantees in terms of performance. Right? I don't know how much value there is in allowing offloading things or logic that do not meet line rate. It is this magic goal, but it has implications that extend, that have cascading effects and also affect a very multi-tenant environment, right? Everybody else essentially who's sharing that piece of hardware. And of course, from the system perspective that you mentioned, Samira, a big question is virtualization. Now you have one switch, you have one top of the rack switch for like 40, 50 servers. The higher up you go, there are even more servers that share the same component. Now, if everybody wants to program it, how much real estate can you dedicate to each of them? Right? Yeah. And you need this is again a completely new field. It's virtualization at a very different level at very different latencies. You cannot afford to spend milliseconds to reconfigure. Right? It has to be just seamless in a data center environment always.
Yeah. So I think there are two things. The first that I am hearing from you guys is like, well, it's very easy to program when you have a C-like interface and then you can just program it. I think that's actually not true, because what we see as a networking person, C is insanely hard for us. Like it's insanely hard to write something in there and then compile it onto a switch. So that's why this whole effort of like coming up with a match action table and then just giving these networking people like a logical view of like, these are packets coming in, you transform them into headers. And then the abstraction basically is like what headers you want to match on and what action you want to do on them, like replace something, increment a TTL or decrement a TTL, do some counting and so forth. So by definition, like if you're talking about the end-to-end like the systems part of it, the way I have seen in networking is like the underlying hardware abstraction, because so restrictive, has actually helped us define this abstraction for the networking community. So I don't know whether in the future, like what other high-level abstractions will pop up, but again, by just looking at the native abstraction of the switch, it seems very amenable to how a networking person thinks. Like I have packet coming in, I want to match on some field and I want to do certain actions. So again, from the systems point of view, it's a very, like what we have seen over the past 10 years, it's like this is the right abstraction for a networking person to express his things. Now, if you ask me to actually replace that and say, oh, this is actually hard and like having something C is much more easier for me to program in, from a systems person, yes, it might be. For me, it's insanely hard because I don't want to know how I'm like sort of building my cans in C. What data structures am I using in C? What cores? How am I allocating my cores? How am I allocating my memory and all that other parts when you build a system? For me, what I want to give you is just, this is a very basic pipeline. There's a parser, match action table, and a deparser. Now just run it on the underlying target. So the underlying target can be like a software-based switch, like a virtual switch in typical data centers, or it can be a hardware or an FPGA or some other smart NIC. So that's my understanding. So I just wanted to raise this point out, like C is not easy. C is insanely hard. We want to go away with that as a networking person.
Yes, but from what you described, again, it seems that you as a networking person, you have this underlying assumption that I write this code and it is going to operate at this, it is going to meet this timing requirement.
Yeah.
I'm talking about C. I just write this code in C. This is the functionality, and if it doesn't meet line rate, whatever, right? But I have the flexibility to just not learn a domain-specific language, or basically I don't have any limitations imposed by this specific domain-specific language, right? I can perform fast Fourier transformation on every passing packet because I just write a function for it, and I can just throw it into the programmable logic. But it's not going to work from a practical perspective.
Right.
I understand your point that yes, if I have this language that was designed for this purpose, it is actually easier. If I understand the language, it is easier to write some code that will fit on that architecture.
Yeah.
And I was just saying that I don't, in my opinion, that is like breaking that type of guarantees from the interface or the language that is used to program this kind of hardware is not a good idea. Because it is actually easier to get these guarantees from the way you express your logic than have absolute freedom and then, as you say, have to think of how is this going to go into a CAM? Is this going to go into SRAM, into the memory? Do I have to go over the PCI every time this thing is accessed?
Yeah.
But if we have some general purpose core, like does not that, it may, so I feel like then it actually makes sense that you should be able to write your Fourier transform and run it on each packet, right? Like what is the issue there?
So I think there are dual objectives here right now. One is performance. The other is the ease of like expression from the user's point of view. So from the architecture side, I want performance. I want to run at very high speed. And from the user's point of view, I want to be able to express this in the least amount of like effort possible. So if you have a general purpose core, you can still define the same abstraction like a match action table on top of it. But then, like what Alex said, it's very hard to guarantee the performance of that system. Like, okay, it's going to meet a certain performance. So that is one part to it. Like the other part is like, okay, you can have a very restrictive architecture like RMT, but now you want to do something more complicated. So from the user point of view, it's very hard to express that now. And both are actually happening in networking community. If you see, people are now using these sort of P for abstraction to sort of use it for doing much more complicated tasks. Like they're trying to sort of use this abstraction to do more things beyond just like match action. Can we sort of offload sketches? Can we do consensus using this protocol? Can we do like a machine learning gradient aggregation on using this abstraction? So all these things are happening. So I think they're dual objective. One is like thinking of this abstraction and making sure that you get the right performance, and also thinking of that abstraction and making it easier for the user to express his intent. So again, I think what we call like this thing is like, one is the development complexity and the other is the performance complexity. How do you address that? I think, again, if we see in the sort of the business domain, like where we have like these databases, the abstraction that they give is very different from the underlying architecture that is running it, which is typically a CPU or maybe some other hardware. So that's a different domain. Like, again, we need that abstraction, like SQL like language to be able to express our queries much more concisely. We can still do that using C, but nobody does that today. They actually use SQL to express that. So similarly, in the networking space, we can still define our architecture using C, but again, it's much easier and to actually do that, and much faster to do that for a programmer using P4. And from the architecture point of view, again, there is no limit. Again, P4 is now compilable to many different architectures, not just designed for the barefoot switches. You can compile it to like FPGAs, you can compile it to software switches. But then from the architecture standpoint, the question is, what guarantees do you want to have from that architecture?
So Alex brought this point of virtualization, and the other issue that I can think of is security and privacy, like coming from the same angle that it's a multi-tenant environment, and all these issues are real issues, like people are concerned about security, privacy, and virtualization. Yeah. So what do you think the future will look like, or what are the challenges to address in terms of those?
Right. So one way I think is to explain this is like, I will use an example to explain how people can do it today. I don't know how general that example is for like a large scale virtualization, but just to give you an example, like today in the public cloud, the thing, if you want to do like one-to-many communication, the underlying infrastructure, like the network doesn't support native multicast. Like it doesn't allow you to do multicast, because the reason there is like these multicast group tables in these hardware switches are very small. Like they're like 5,000 entries or 10,000 entries. And if you're running in a multi-tenant environment, the number of distinct groups that you may need may actually exceed like millions of like unique destinations or millions of unique one-to-many communications. So you cannot just take all of those millions of distinct one-to-many communication groups and put them into a switch, because the switch does not have that much space in there. So the question is like, how can you virtualize this space? Like again, when you're running in a multi-tenant environment, I call this as the multicast state. So you have a certain multicast state based on the number of tenants you're running in a network. How can you take that state and push it into a network? What's the best way? How can you scale it? Today, like you cannot, like using these existing switches is very hard. Like it's again, if you want to do like some kind of aggregation, like prefix aggregation, you take two different group IDs and compose them together into one and then map it down into the switch. It adds a lot of overhead, both in terms of the load on the controller. Like whenever a tenant changes, the other tenant has the rules for the other tenant have to change as well. So it doesn't hold this sort of again, an invariant that they have is like the two tenants are actually isolated from each other in terms of performance and so forth. So how can you scale it, or how can you virtualize it? So the one way to do this is like, if you look at the network today, switches are not just the only entity that can maintain state. Packets themselves can also maintain state, and they can also carry state. So if you have a certain level of programmability in the switches, you can actually program them so that they can now read the state from the packet itself rather than from within a switch, like within a switch itself. Because now what happens is like, rather than maintaining a globally shared state, it becomes a local state. Like each packet is carrying only its own state. You match on it in a switch, and then you route the packets all the way like to the destination. So that is one way of scaling your state within a network. Like it's like rethinking, where do you want to encode it? Again, how general it can be, we'll see what other use cases can come up. And then also in terms of like security, it again depends on, like, if you look at a typical cloud data center, it's not just a physical infrastructure, it's also these virtual hypervisor switches running in each end host. So it's not like you're exposing the details of your underlying physical infrastructure to a tenant. What happens, like whenever a tenant sends a packet, the hypervisor switch, which is also still in the data center domain, can actually do a lot of filtering for you. It can see, okay, if a certain packet is being sent many times into the network, it can detect DDoS and throw it before even sending it out onto the physical network. So what I'm trying to get at is like, we may have to revisit the whole like sort of space, and like, unlike the way we do virtualization in the end host, it may not be the same as doing it in the network. We may have to rethink as to how do you scale state, where do you encode it, where do you apply your security policies, how do you have to apply it, and all these other things. So I think one approach that we did some work on was, how can you scale multicast in a public cloud? How can you make it possible? And the basic question there was, you have a huge amount of multicast state flowing in the network. Today, they want to try to encode it using switches as the only means of maintaining state. But if you go beyond that and think of packets as state carrying entities as well, you can actually scale to infinite amount of groups. There's basically no limit on how much state you want to route in the network. So that's an example. And again, I don't know how general it can be, but that is one way people can think of virtualization, scaling their state in the network, and also applying security policies in these public clouds.
Yeah, I think that's a very interesting take, that actually even I haven't thought about it, that the security or the virtualization should be thought of per packet instead of the traditional way we think about it.
Yeah. Because the traditional wisdom was switches are the only means of carrying state. But then if you think of switch as the mean of as the mechanism, as the only entity carrying state, then all the tenants will need space within that switch for themselves. And that's a huge sort of task or requirement from a switch. Like if you have hundreds of thousands of tenants, that means like, if you want to even give one rule to each tenant, then you need 100,000 rules in the switch. And that's a very hard sort of thing to implement today. So the other way is like, why not just make it part of the packet itself? Because then it's local, And the nice thing there is, like, unlike switches that have to maintain state for all the tenants, a packet only has to carry its own local state. It does not have to think about what other tenants are doing or what other state they have to maintain.
So doesn't this depend on how quickly you can, essentially, if the packet carries a rule, that sounds like an awesome idea, actually. And essentially, you're trading off bandwidth. The rationale, I assume, is that you have ample bandwidth is not really the problem here.
Yeah.
How quickly can that rule that you're carrying be deployed on the hardware, though, right? Because presumably there has to be some setup, right? You need to set up some processing pipeline.
So the thing is, like, again, because the rule is being carried in the packet, so the thing that changes is the rule itself and not the program that you have programmed once or written once for the switch. So for the switch, it's always the same. Like, whenever a packet comes in, if it matches that switch ID, it reads that rule, apply that rule, and then goes on. You don't, like, whenever a change happens, it only happens within a packet. You don't have to go and change switches. They're just, it's going to be a new value for them. So they will say, okay, this is the packet. Again, this is my switch. It's coming here, and this is the sort of action I need to perform on that switch itself. So basically, just like when you are writing rules in a switch, you only change the rules, not the overall P4 program. Here, those rules are now in a packet, so you only change the rules at runtime, not the P4 program that is operating on those packets. So change is very fast, I think, in these kind of operations. You just compile your P4 program once, let it know, like, whenever this packet carries your ID, just apply that operation. So for example, for multicast, what that means is, like, if this is my switch ID and this is the port list that is telling me which output port I have to go out to, just read those port lists and send the packet out. That's all. Next time, if another packet comes in with your switch ID and it has a different port list, just send the packet out on those port lists. If you want to do something more complicated, then we may have to revisit, okay, if there's a change that needs to be done in the switch. But the whole goal here was, like, as long as you can move the state out of the switch into a packet, you won't need any change in the switch itself, because switch is stateless. The only thing that changes is state, and state is in the packet.
That's interesting. Yeah. So last question. So it feels like there is a lot of new problems and research challenges ahead in this direction. And I would like to ask that what type of collaboration or what type of expertise do you want from the other community? So for example, Alex, having the background in systems and architecture, like, what type of things do you want from the network community? And on the other side, how we architects can help the network community. What do you want from the architecture community? So let's start with Alex.
So I think it is very important for us as architects to have deeper insights and maybe, you know, feedback from the network community on more core network issues, right? The protocol. So I've been thinking about protocol extensions and hardware modifications and stronger guarantees from the network itself that, however, have implications if you want to make these changes when you deploy these protocol modifications, let's say, and you relax some assumptions. For example, say lossless network fabric, right? This is a very strong assumption that many people are making, definitely architects are making. And yeah, you can have a much linear network protocol if you have these guarantees. But of course, you can always focus on, you say you make an assumption and you take it from there and you design your architecture. But it would definitely be stronger if it were a collaboration with actual core networking people to make advancements in these vectors as well, right? So the resulting co-design does not only have an architecture angle, like, oh, if I integrate my network interface and I make these simplifying assumptions about the protocol and the network, I can demonstrate these benefits. But to have the biggest impact would be to actually go and deploy this in a data center environment, or at least be able to simulated at a network, at the data center environment. And that scale actually comes from the core network itself, including all the switches, all the routing, congestion management. These are things that definitely networks people have much more expertise than architects. So I think that is a good point of collaboration, to have this vertical solution, to go from specialized endpoints to specialized endpoints that are well integrated with the whole ecosystem of the data center network.
So for the networking people, and again, just to say out loud, like I think of myself as an architect as well, so I'm purely not a pure network person. So I just take this.
So now you have become both.
Yeah,
I have to. So I say to my students that nowadays more networking people work with FPGAs than actually architects.
Yeah. So I think from the networking space, again, I think from one thing that we are doing, I'm not sure how to say like what expertise we need from the architects, but again, clearly we need these expertise where as we are moving away from the switch architectures to closer to the end host systems, again, how can we integrate them? And again, just what Alex said, like if we reverse that thing, like we are the core architecture people, we are building something from the network point of view, and we make certain assumptions from the architecture, like the architecture can finish things and do certain processing in a such and such way, then what can we do in the network? So I think there's a very nice, like sort of cross collaboration point here where assumptions that we are making from the architecture standpoint, folks from the architecture community can help us validate those. And similarly, assumptions they are making from the networking standpoint, folks in the networking community can help them validate those. And then we can combine forces and move on and see how we can build systems. But again, I'm not sure, like, there's also, I think, unlike the typical von Neumann architecture, like the end host machine, we also have switch architectures. And again, those switch architectures typically come into the networking community itself. I don't see many people working like in the pure architecture domain on these switches. But there's a huge research, and maybe folks who are pure architects can actually come in and help us define this ISA and the kind of like operations that we want. So for example, is a VLIW architecture makes sense, which is a match action table with a single cycle VLIW pipeline? Or can we actually replace that with a more SIMD-like architecture with more vectorized operations and still be able to meet the line rate invariant? Because again, we have this magical requirement and we are trying to build architectures, but maybe the core architects force are in a much better position to help us sort of devise those kind of new abstractions and define what can or cannot be done in these switch-like environments. So that is one space. And just to like bring in again on the notion of cross collaboration, there is also like we need collaboration from other people, like in, for example, ML folks who are building. So they need to come in and help and work with us. Like given that if we are talking about new primitives and operations, to, for example, make these switches intelligent. First, the question is like, yeah, it's a good goal, but does these features or data that we are collecting within a network have enough predictive power or not? So we need these ML folks to come in and help us and build these models and show that, okay, if you're running in a network-like environment and you're collecting these state from within a network, we can actually collect this and do much more intelligent decisions about routing, load balancing, congestion control. And to do so, first of all, we need to validate that part. And then once that is validated, we can then go in and come up with new primitives to show how can we run a part or a piece of a machine learning model within a switch to replace these existing heuristics like ECMP or random load balancing with a much more informed model. So there's a lot of like cross collaboration that is happening from architectures to systems to networking to ML folks, and they all have to work together to fully realize this like fully autonomous self-driven networks, like just like on the notion of self-driving cars in the coming year. Yeah.
Yeah, like I feel that we have really exciting times ahead, and hopefully there would be more and more collaboration. Like the viewers who will watch it, I would highly encourage them that like Shahbaz and Alex, both of them talked about so many open problems that it's really interesting that let's see what happens in the future.
Yeah. But I think it's an interesting time. Yes. Like a lot is changing. And again, I was not bringing up the Moore's law point, but again, Moore's law sort of is slowing down and dying, and that has actually been opening many other avenues, not just in the architecture space, but also in the networking space. So let's see how and where it goes.
Okay, let's end with Moore's law.
Yeah.
our favorite topic.
Sounds fitting.
Yeah.
Thank you for your time. I really appreciate it, and it was really an interesting discussion.
Thanks,
Cool.
Samir.
Thank you so much for
Thank you for organizing this.
yeah. Thank you for having us.